Welcome, everyone. In this session, we're going to explore alternating current circuits, or AC circuits, a domain where signals fluctuate in time, react to inductance and capacitance, and introduce us to entirely new forms of energy dynamics. Our goal is to not just memorize formulas, but to build an intuitive, physics-driven understanding of what's truly happening in these circuits. Let's begin with the fundamental question. What is alternating current? Alternating current means the direction of charge flow changes periodically over time. It's sinusoidal in most practical systems, especially in power systems. But why sinusoidal? Physically, sinusoidal waveforms emerge naturally from rotating systems generators, for instance, which rely on rotating coils inside magnetic fields. According to Faraday's law of induction, this rotational motion produces a voltage that varies sinusoidally with time. Voltage of time is equal to maximum voltage amplitude times sine of omega t plus initial phase angle. Here, omega is the angular frequency and phi is the phase angle. Let's define the key measurable quantities in AC. Peak value is the maximum amplitude of voltage or current. RMS, or root mean square, is the effective value that does the same work as a DC source. Mathematically, for a sinusoidal function, it is equal to maximum amplitude divided by square root of 2. Frequency is defined as the number of cycles per second measured in hertz. Time period is the time for one full cycle, where period is actually the inverse of frequency, meaning t is equal to 1 over frequency. In DC, electrons move steadily under a constant field. But in AC, the field oscillates, meaning electrons are pushed and pulled back. They don't travel far, but they vibrate in place. This back and forth motion interacts with magnetic and electric fields in capacitors and inductors in complex but predictable ways. Let's understand those reactions. A capacitor stores energy in an electric field. In DC, after it's charged, it acts as an open circuit. But how it works in AC? Electrons oscillate, constantly building and collapsing the electric field. As a result, current flows continuously even though no electron physically crosses the dielectric. The capacitor leads the voltage by 90 degrees. Why? Because the current is proportional to the rate of change of voltage. Or in mathematical language, we have current at any time is equal to C times D of V over dt. A sinusoidal voltage leads to a cosine-like current, hence the phase shift. An inductor, on the other hand, stores energy in a magnetic field. In DC, once current stabilizes, it acts as a short circuit. In AC, the inductor resists changes in current because of Lenz's law. The induced voltage always opposes the change that created it. The voltage across an inductor is equal to L times D of I over dt. Thus, voltage leads current by 90 degrees. Therefore, the inductor delays the current's rise and fall. In AC, we generalize the concept of resistance to impedance, denoted by letter capital Z. Impedance captures both magnitude and phase shift. Each component has a different impedance. Resistor has the impedance equal to its resistance. Capacitor's impedance is equal to 1 over j omega c. And inductor's impedance is equal to j omega L, where j is square root of -1 and omega is 2 pif, which is angular frequency. Impedance lets us analyze AC circuits algebraically, just like DC, using phasors. Let's put it all together in a series RLC circuit. A resistor R, an inductor L, and a capacitor C, all connected in series to an AC source. The total impedance is equal to R plus j omega L, j over omega C. You now get a resonance frequency when omega L is equal to 1 over omega C, which means our resonance frequency is 1 over 2 pi times square root of LC. At this frequency, inductive and capacitive reactances cancel each other out. The circuit behaves purely resistively, and current reaches maximum amplitude. This is the basis of radio tuning, signal filtering, and even Tesla coils. Let's go over an example. We have a circuit that includes a 100 ohm resistor, 159 millihenry inductor, and 10 microfarad capacitor, which are connected in series to a 50 hertz source. We want to find impedances. We know that the total impedance is equal to impedance of resistor plus impedance of inductor minus impedance of capacitor. The impedance of resistor is equal to the resistance, which in our case, it will be 100 ohm. The impedance of inductor is equal to j omega L. which means 2 pi times 50 hertz times 0.159 Henry, which is about 50 ohm. The impedance of capacitor is 1 over j omega c. In this case, it is equal to 1 over 2 pi times 50 hertz times 10 to the power of minus 5, which is about 318 ohm. Therefore, our total impedance will be 100 minus J268 ohm, which means the amplitude of impedance is 286.5 ohm. Now, if need, we can use Ohm's law to find current and calculate power components. In the next session, we'll look at how we actually measure these AC quantities with instruments, including RMS meters, oscilloscopes, and power analyzers. Until then, revisit your fundamentals and remember every sinusoidal signal is a window into rotational energy, field interaction, and time-symmetric physics.